Hello and welcome to my lecture series for Control System 1. Myself, Sumon Ghosh, Assistant Professor from Department of Electrical Engineering, Guru Nanak Institute of Technology, Kolkata. This course, that is Control System 1, is for 5th semester BTech Electrical Engineering student. And this is our 5th and 6th lecture PPT. And in this lecture, that is lecture 5 and lecture 6, the following contents we will discuss. The contents are as follows, like analogous system, force voltage analogy, force current analogy, and related workout problems. So moving to our first topic, that is analogous system. Now what is analogous system? As you can see the definition, two systems are said to be analogous if they are identical to each other in terms of mathematical model. Okay, suppose there are two differential equations and the parameters of the two equations are different, but the form or the order of the two differential equations are same. Then we can relate them and set them as a analogous system. Now let us take examples, like in our previous lecture we see the translatory mechanical system. What is translational mechanical system? In translational mechanical system, the motion of a body is along a straight line. Okay, and there are three elements, that is spring, that is K, mass, that is M, and damper, that is B. And the force equation of the spring mass damper system, we already discussed that how we can calculate the differential equation or the force equation of a spring mass damper system. For mass, the force will be m d2x dt square, and for damper the force will be b dx dt, and for spring the force will be kx. And if the total force applied to the system is small f, then this total force is divided into spring, mass, and damper. So we can write the differential equation as, which is shown in equation number 1, that is small f is equal to force due to mass, that is m d2x dt square, plus force due to damper, that is m d2x dx dt, and addition of force due to spring, that is kx. Okay, where m is the mass, b is the damping coefficient, k is the spring, stiffness of spring, x is the displacement, and force F is the force applied to the system. Here we apply the force F, that's why the displacement is occur. So here F is the excitation element, so F is the input and X is the output. We apply here force, that's why displacement is occur. So that's why we say that force is the input and x, that is displacement, is the output. So that's how we get the equation number 1. Next moving to our next point, that is force voltage analogy. Why it is called force voltage analogy? Before understanding this, Let us take a RLC series circuit with a excitation voltage small e. Here small is the voltage, R is the resistance, L is the inductance, and C is the capacitance. So for this RLC series circuit, if we write down the KVL equation, then the equation will be total voltage applied, that is small e, is equal to drop in resistor, that is Ri, plus drop in inductor, that is L di dt, plus drop in capacitor, that is, or voltage across capacitor, that is 1 by C I dt. So now, this is the equation, L di dt plus Ri plus 1 by C I dt is equal to E. So this is the KVL equation for this RLC series circuit. Now we all know that according to definition of current, I is equal to dq by dt. That means current is the rate of change of q. Q means charge, rate of change of charge, that is current. Now if we put the value of I, that is dq dt, in the previous equation, then the previous equation become L d2q by dt square plus R dq dt plus q by C is equal to E. So this is our equation number 2. And if we compare, now going to the point, that is why it is force voltage analogy. Now if we see the equation number 1 and equation number 2, then you can see that in equation number 1 the excitation element was force, that is small f, and equation number 2, here the excitation element is small e, that is voltage. So comparing equation 1 and 2, equation 1 and 2 are two differential equations, but they are mathematically identical. Okay, just look equation number 1 and equation number 2, you can see that the two equations are mathematically identical, but the parameters are different. Okay, if we compare equation number 1 and equation number 2, then you can see that in equation number 1, which is force, in equation number 2, that is voltage. That's why this equation is called force voltage analogy. That is, in equation number 1, which is force, in equation number 2, that is voltage. So that's why it is called force voltage analogy. Next, moving to our third topic, that is force current analogy. And in this force current analogy, we have to take a RLC parallel circuit. Okay. Now, and we apply here a current, that is small I, and this small I is divided into three branches in R, L and C, that is IR, IL and IC respectively. And according to KCL equation, we can write the total current, that is small I, is equal to IR plus IL plus IC, that is summation of the three branches current. Now small I is equal to IR. IR means, now according to Ohm's law, I means V by R, that is here, that is E by R, and IL is 1 by L E dt and IC is C into dE dt. Okay, very simple. We can get this from KCL equation. Now According to Faraday's law of electromagnetic induction, we can write the voltage, that is EMF, is equal to d phi by dt. Okay, now put the value of E, that is d phi by dt, in our previous equation, and we can get the equation, that is C into d2 phi by dt square plus 1 by r d phi dt plus phi by L is equal to I. That is equation number 3. Now here it is called force current analogy. Now why force current analogy? Now if we compare equation number 1 and equation number 3, then we can see that in equation number 1, which is force, in equation number 3, that is I, that is current. And equation number 1 and 3 is mathematically identical, but the parameters of these two equations are different. Now if we compare the parameters, then we see that equation number 1, that is F, in equation number 3, that is I, current. So that's why it is called force voltage analogy, with comparing to the translatory mechanical system. Now moving to our fourth topic, that is rotational mechanical system. We already calculated, or we already see how a rotational mechanical system works in our previous lectures. Now what is rotational mechanical system? In rotational mechanical system, the rotation or the movement of the body takes place along a axis. That's why it is called rotational. Okay, now in rotational mechanical system, let us take one example, that is K means stiffness of the spring, theta is the angular displacement, J is the inertia constant, and T is the torque applied, and B is the damper. Here the friction is considered as a damping element. Now if we write down the differential equation or the torque equation for the following figure, the equation will be like that, that is total torque applied, that is capital T, is equal to J d2 theta by dt square plus B d theta dt plus k theta is equal to total torque applied, that is capital T. Now this equation 1, 2, 3 and 4, just look the 4 equations, all the equations are mathematically identical, but their parameters are different. Now if we compare that 4 equation, now in equation number 1, which is M, in equation number 2, that is L, and equation number 3, that is C, and equation number 4, that is J. And like this way, in equation number 1, which is F, in equation number 2, that is E, that is voltage, equation number 3, that is I, that is current, and equation number 4, that is torque. So if we compare the 4 equations like this way, then we can, and after comparing, if we form a table like a chart, then we can get like this. Here 4 columns are there. First column is translatory mechanical system, next is translatory rotational system, next is force voltage, that is FV analogy, next is force current analogy, that is FI analogy, and we can see the relation between parameters. In translatory system, which is M, in rotational system, that is T, and in FV analogy, that is voltage, small e, and in Fi analogy, that is small I. Like this way, we can compare all the parameters and we form a table for our better understand. Okay, so this is a very important table. You have to remind, or you have to go through this for your exam purpose or for your problem solving, which we will solve in our next slides. Now moving to our first example. Moving to our first example, that is, here one spring mass damper system is shown, and the question was, draw the electrical analogous circuit using force voltage analogy for the mechanical system as shown in figure. Here one mechanical system is given and we have to convert this mechanical system to a electrical system. That is the basic thing we have to calculate. Here one mechanical system is given, we have to convert it in electrical system. So what is the process? Now, in our previous lecture, when we calculate the transfer function for a mechanical system, there we draw first the mechanical circuit diagram. The same process we have to do first, that is, we have to draw the mechanical circuit diagram first. Here in the mechanical model, there was two displacement, that is x1 and x2. So there will be two nodes in the mechanical circuit diagram, and the two nodes are connected through K2. Like this way, how we can draw the mechanical circuit diagram we already discussed. So now I am not going to that point. So here we got the mechanical circuit diagram like this, that is, with node x1, m1, b and k1 is connected and force is also connected, and in node x2, k2 and m2 will be connected. Okay, so that's all for today's class. Now just look at the problem. We will solve the other part of the problem in our next lecture. So just go through the previous lecture, that is lecture 3 and lecture 4, and first understand how we can draw the mechanical circuit diagram from our mechanical model. If we understand that thing, then we can solve, or then we can follow the next step of this example. So just go through or just see the lecture 3 and lecture 4 videos first. So that's all for today's class. In our next class, we will discuss how we can solve this type of problem and how we can get the electrical model from this mechanical system using force voltage analogy. So thank you so much. Thank you for watching.